Hi guys, so today we'll be talking about second order systems. We are diving into the world of second order systems, and we will be talking about analyzing a series RLC circuit. Alright, so when we meet a resistor, an inductor or a capacitor in a second order system, how are we going to deal with these series of components inside the circuit? So my colleagues are going to help us dive more deeper into the mathematical components of this very subject matter.
Thank you, Solomon. I'm in the person of Mother Kelvin Malloy, and I'll be talking about the Series RLC circuit. So what is the Series RLC circuit? So the Series RLC circuit is a fundamental building block in electronics consisting of a resistor, a capacitor, and an inductor connected in series to a voltage source. So to determine the behavior of the circuit, we have to consider two properties. So these properties are the resonant frequency and the impedance characteristics of the circuit. And understanding these properties is going to help we, the engineers, predict how the circuit is going to respond to different signals. So I'll hand over to my colleague Walter to take over from here. Thank you.
Hi, I'm Walter, and for this specific analysis, we are working with these parameters: a resistance R, which is equal to 1 kilo ohms, an inductance L, which is equal to 10 millihenry, and a capacitance C, which is equal to 0.01 million farads. The main objective of this whole problem is to analyze the circuit to determine the undamped natural frequency and the damping ratio.
Hi, I'm Precious Anna, and I'll be talking to you about the component voltage relationships. To understand how the circuit behaves, we need to look at the voltage across each component. So let's start with the resistor. Its voltage is directly proportional to the current flowing through it. And we also have the inductor, and its voltage depends on the rate of change of that current. We also have the capacitor, whose voltage is based on the accumulated charge over time. And these three unique behaviors combine to dictate the total circuit response. Thank you.
Now, to make this easier to solve, we differentiate the entire equation to eliminate the integral, giving us our second order differential equation. When you want to find the natural response, we set the input to 0. This homogeneous equation describes how the circuit responds using only its internal stored energy. Thank you.
So to start our derivation, we take our homogeneous differential equation and divide every term by the inductance L. This simplifies the equation to form d square I over dt square plus r on L di dt plus 1 on L ci equals 0. To solve this equation, we assume a solution for the current in the form of I of t equals e exponent st. By substituting this into our equation, we arrive at the characteristic equation s squared plus r on ls plus 1 on lc. System dynamics, we compare these results to the standard second order form, which is s squared plus 2 zeta omega ns plus omega n squared equals 0. By comparing the coefficients of these two equations, we can directly identify two critical parameters for our circuits. that is one, the natural frequency, which is the omega n, and also the damping ratio, which is zeta. This type of oscillation is very important because it moves us from a basic circuit descriptions to a mathematical model that tells us exactly how the system will oscillate or decay before we even plug in a specific component's values.
Okay, everyone. It's another mouthful, and I'll be taking us to slide 10 and 11. Okay, so now that we have a derived characteristic equation of the system, we can now move on to extracting two very important parameters that describe how the circuit behaves, which is the natural frequency and the damping ratio. Let's begin with the undamped natural frequency, which is denoted by omega n, right? From the standard second order form, we know that omega n is equal to 1 over the inductance times 1 over the square root of the inductance times capacitance. This parameter represents the frequency at which the system will naturally oscillate if there was no resistance in the circuit, meaning there will be no energy loss. Substituting the circuit values, inductance is equal to 10 millihertz, and then capacitance is equal to 0.01 nanofarads. We obtain the final results become 100,000 radians per second. So to make it simpler, we convert it to hertz, then we get 15.92 kilohertz. Okay, so next we have to determine the damping ratio, which is denoted by zeta. The damping ratio tells us how quickly the oscillations decrease over time due to energy being dissipated by the resistance. The formula is equal to zeta. The formula is zeta is equal to the resistance divided by 2 times the square root of the capacitance over the inductance. After substituting the given values, including the resistance, which is 1 kilo ohms, we obtain the damping effect, which is zeta, to give us 0.5. This value gives us important insight into the circuit's dynamic behavior. A damping ratio of 0.5 indicates the system is underdamped. In this condition, the circuit will oscillate, but the oscillations will gradually decrease in amplitude with time. In many engineering applications, this type of response is useful because it allows the system to respond quickly while still remaining stable. Therefore, by calculating these two parameters, which is the natural frequency and the damping ratio, we can already predict how the RLC circuit will behave even before observing its actual response. Thank you.
Thank you. So I'm casting some of from biography. So what does damping ratio of 0.5 mean? Since it is between 0 and our system is overdamped. This means the circuit will oscillate, but the amplitude will decay over time. These parameters are vital for engineering stability and frequency selection. Thank you for watching, and as we say in engineering, it's the craft of turning physics